My first parallel programming project. The topic was matrix multiplication, but specifically implementing a tiled algorithm to try to improve the performance on the GPU. So I'll first run a couple of these guys. I'm first going to compile. Uh, this is here because I'm using some of the CUDA standard libraries, which are elsewhere in this server's file system. And then we'll run. As I'll show you shortly, this randomly chooses the dimensions, and all of the instructions randomly decide element values for the matrix multiplication. And then here, there's stats on the GPU side of the computation, and then the CPU side of the computation. By side, I mean I'm running the naive CPU matrix multiplication versus my tiled matrix multiplication on the GPU. As you can see, there's an enormous difference in gigaflops, which is a great thing to see. And then here, I decided to print out these like pseudo errors for any time that the CPU value was farther than 10 to the negative sixth from the GPU answer. Obviously, this is to be expected. I spoke with a handful of people, including my professor, and it seems like that's standard between the differences in the machine and how they compute numbers, but also, that was it. I know there are ways to get around that. Like maybe I could run the GPU, I don't know, 30, 100, 1,000 times and then average out the results. But in this case, I didn't. Although, as you'll see shortly, I do run the the GPU algorithm several times to get good statistics because it seems like there's a lot of variance when it runs. But anyways, we'll get into the code. As we can see here, these are all of the CLI variants. There's the random dimension initialization, and then all of these assume random element initialization. And then here you can specify your 3 dimensions in this case because in order for matrix multiplication to work, the number of rows in your first matrix needs to be the same as the number of columns in your second matrix. All right, so I mean, kind of trivial on the CLI side of things. Here we are doing the initial setup, all the memory initialization, all the memory initialization or declaration, I guess. And then here I define the number of iterations that my GPU is going to run, how many times the GPU is going to run my algorithm. And the reason I do this is just to, again, kind of cut down on the variance so we get a more specific or more realistic average for the performance. And then here we just print out the message that we saw before here. And then very similar, the naive CPU algorithm and doing very much the same. Then cleaning up everyone. I guess the real interesting part is the CUDA kernel itself, where I mean it's generally pretty simple. I made some variables to handle the specific threads information to make my life a little bit easier. And then here, since it's a tiled algorithm, essentially what we're doing is we're selecting some little submatrix in our output matrix. And then we're going to iterate through the length of the shared dimension in order to compute the actual output. So to be more clear, say our output matrix is, I don't know, 1,000 by 1,000, and our tile width is 32 by 32. We're going to have every block is going to calculate a single 32 by 32 submatrix of our output matrix. And then because we're only working with 32 by 32 so 1,024 threads, we need to iterate across the, I guess, 32 vectors, each of which are, I guess, 32 by the shared width, or vice versa for the other matrix. Hopefully that makes some sort of sense. But this is a very traditional tiled algorithm. And here, this is where we're iterating over the shared width using the dimension of our tile. This is initializing shared memory. Obviously, we have to be careful of divergence. Divergence issues is a huge problem on the GPU, so we want to make sure that we keep as many threads doing the same thing in the same warp as possible. And here, these are just the condition checks to make sure that we're computing our actual values, because there's a chance that our matrix isn't a perfect, or even it doesn't evenly divide get evenly divided by our tile width. Then here's the actual computation. And here's our saving. We sync threads to ensure that the shared memory is fully initialized before we start the computation. And then we sync threads because after the last guy, we need to make sure all the computations are done before we save. But yeah, it was a super cool initial project. I'm going to flip over to my local copy where I can't actually run it because I don't have the access to the GPUs. But I'll show off the lab report I made. Here we're just talking about basic mathematics. I guess really I'm interested in showing the results. So here you can see the difference. Note that the matrix dimensions scale exponentially, which is kind of why you see a logarithmic shape. But here I plot the dimensions versus the gigaplop output of the GPU for varying block widths or tile widths. As you can see, you may expect, if you're familiar with the algorithm, that the bigger blocks perform better with at least bigger inputs. Here's some just preliminary stats, some speed up stuff. And we have 5 of these GPUs on the server, so that might center your expectations a little bit. But yeah, super cool start. There are going to be a few more projects coming up, so I guess look out for those.